So welcome to MGM course, and we were doing neural networks. So I defined perceptron and simple MLP, but what really becomes interesting is when we go for deeper neural networks. So I will just define deep neural network. There's nothing too much compared to the MLP. Okay, there's it's just maybe some few notations that I will add. Okay, so I call this part 2, and again I take some slides from my favorite source, which is deep learning at CMU. It's pretty good course, so I acknowledge some of the figures that I take from there, and you are advised to go and maybe if you want to learn deep learning really well, I highly recommended that you go there. One of the best explanations of CNN, RNN, and attention-based models. Okay. Okay. So for our purpose, what we really need is how to just use them rather than doing research on the architecture itself. There are one or two places where, in fact, you might do a bit of architecture engineering. Okay. There's something called invertible one-by-one convolution. So there are some ideas like that, where you want to kind of invert the probability distribution for generative tasks. Okay, so but we will have one class on that, but otherwise you are just supposed to use them. Okay, so if you look into neural network, last class we saw multi-layer perceptron. Now you can see that they can be like complicated like that. There are more layers. So I mean, even this 3 layers, hidden layers, are not that enough. So let me introduce the typical notations that people use. Okay, so this is called input unit. This is not seen as a perceptron, okay, because there is no activation or linear combination happening. This is just input. Okay, so you see them as input layer. So this could be a set of pixels. Okay, it could be basically any data that you want to learn, and these are the first hidden unit. Okay, we call it hidden because input we know exactly what is going on, but these are hidden because then there is a weight, linear combination, activation. So you don't necessarily explicitly know them. Okay, if you print the values, you will know obviously, but as such, it's hidden from us. These are hidden. Okay, so these are called hidden layers. So this is your first layer, hidden layer. This is your second hidden layer. Okay, this is your third hidden layer. So this is a deep neural network with 3 hidden layers. Okay, input layer and output unit. Okay, so here we are just fetching the output basically. Okay, so again we don't want to have any perceptrons here. These are just output values. Okay, until here we had activation and we are producing the final output. Okay, so these are the terms used. Sometimes people will ask you how many hidden layers you have in your architecture. Okay, and within each hidden layer, how many hidden units you have. Okay, so these you will count. Okay, these many is hidden unit in the first layer, these are hidden units in the second layer, and so on. Okay, and usually it's a directed network. So directed means that edges tail are here and they end up here. Okay, so the head is here. So that's why we can see this as a directed graph, and it's always going forward. Okay, there are architectures with the feedback loop. We can see them as feedback loop, but for the moment you see them as directed network. Okay, so there are no loops also in a basic deep neural network. There are no loops. It's a directed network. Inputs are sample features. As I said, features could be like image features, text features, okay, any like audio features, okay, spectrogram features, and so on. And output depends what you're trying to do. Okay, it's classification. Then it will be some probability of the class that you want to predict. So as I said, hidden units, intermediate units are hidden units. The network is called layered because there are many layers. Okay, and these ones are called layers. Okay, the vertical. So we see them as layers. Input is input layer, output is output layer, intermediate layer is called hidden layer. Deep network is a network with many hidden layers. Okay, so there's no such thing as when we call it deep. Okay, so we don't say okay beyond 10 we call it deep, or but it's a like implicitly known that there are many layers, then we call it deep neural network. Okay, so typically it's not. I mean, typically you may have like more than 10, or okay, it depends. Again, it depends on the problem at hand. You may not want to have very complicated model for something which is simpler. So the idea here is that it gets more and more complicated. Perhaps the model needs more complicated representation. Okay, or the prediction function. Okay, so typically that's the scene, but you have to play around. So these are hyperparameters. Okay, when you use this neural network, which type you will use, how many hidden layers will be there, how many hidden units will be there. These are hyperparameters. Okay, you are supposed to play around with the validation test and find out what is optimal in your case. Okay, so and hyperparameters are parameters that are mostly experimentally defined. Okay, that's how we call them hyperparameter. It's very hard to tell you explicitly that those exactly take this parameter, this set of parameter, and it will work. Also, okay, mathematically we don't. So that's why we call it hyperparameter. You find them while playing around with the code. Okay, so it's a fully connected network, at least in the in the initial definition we can say it's fully connected, but then you can do some kind of pruning. Okay, you may drop some edges. These kind of things are also done in some cases. So so you may specify. Okay, if you drop some edges, you don't consider them complete, right? So what is the meaning of complete, right? It's similar to how the complete graphs are defined. Okay, each node is connected to every other node, but since it's a directed graph, this node is connected to all the future one. This node is connected to all the future one. So that's what complete means in this case. So but between the two layers, right? Okay, these guys don't have edge with these guys. Okay, it has only with this, so it's complete in that sense. This guy have all the nodes here have edges with all the nodes here. All the nodes here have edges with all the nodes here, and so on. This is the basic definition. As I said, you can do pruning and things like that and specify, but in the basic definition we assume that it's complete. Edges of the network are weighted. Okay, so there are weights. Obviously, we have seen in the previous class multi-layer perceptron. Obviously, these are the weights, and this is exactly what makes it learnable, right? So we tune the weights for a given problem, and these are parameterized networks, parameterized by the weights between the layers. Okay, so as I said, although it looks complicated as such, it's a complete graph and so on, but it is made of simple features. It is made of simple units like perceptrons. Okay, and as such, we have seen perceptrons are very simple functions. Okay, and what does it do? We recall from the last class that it takes input from obviously from these guys. This is the perceptron we are highlighting, and the input to this perceptron are everything that comes from here, because it's a complete graph for the moment. So it will take x1, x2, x3, dot, 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 xn, and we add one bias term also 1. You will always see this everywhere added. Okay, this bias term is just fixed as 1. Okay, in the coding when you do, you just take these and just add one entry at the end. Okay, and obviously the weight is learnable still, obviously. So weight corresponding to the bias is also a learnable parameter. It's not any constant or anything. So this is what each neuron or perceptron looks like everywhere. Okay, this neuron input will be all these guys. Okay, plus the bias term. So basically, this is a generic thing. Any neuron or like that, except the input and output. Okay, and otherwise, so here the way this figure is, it may be a little bit contradictory to what I said before. Here, according to the figure, this is still a perceptron, and what will be output will be the next one. Okay, which won't be perceptron obviously. So we have to be a little bit correct a little bit according to the figure. Okay, still these are perceptron. They are still processing, and the final output will come next according to this. Okay. So, so as such, as I said, this is very simple. Okay, the only complexity is the fact that it's done many times over. Okay, and if you do it many times over, it can represent a very complicated function because this is just one f, right? But this f is acting on these output of these guys, right? And these guys themselves are coming after some activation of the previous ones, linear combination activation of the previous one. So it's like a very complicated function overall. It's a nested, right? F of okay, linear combination, and then linear combination of that, then f, then linear combination, then f. So there are theorems on that. I will not do that theorem, that such functions can represent are universal approximators. Okay, so given any arbitrary function, we can approximate it to a large extent. We can get closer to a given function. Okay, with a very good very less error. Okay, so that is the reason why these neural networks are very powerful. Okay, now you can throw in audio data, you can throw in image data, you can throw in almost any prediction problem is like learning some function, right? Some very highly nonlinear function. These are nonlinear, right? Why this is nonlinear? Because of the activation function. Okay, if it does only linear combination, then it's a linear operator. It's like some W matrix multiplying to the input vector x. So as such, that is linear. Matrix times vector is a linear function, but then non-linearity comes from the fact that there is a f which is nonlinear. Usually it's nonlinear. You can see these f, some plots are given. Again, you have choices for f, whether you choose sigmoid, whether you use some kind of a ReLU, okay, or some relaxed variant of ReLU, and so on. Okay, so the choices of f is also useful. Last class someone was asking which one you choose and so on after the class, and there are a few reasons. Again, in some cases it also behaves like hyperparameter because you learn from the data. In some cases sigmoid is very good, in some cases ReLU is very good, so it is still a hyperparameter. Okay, so there are cases where ReLU is good because it prevents maybe let's say gradient exploding gradient and so on. Okay, because when you train and if you use the chain rule, you have because of the chain rule you have gradient of the gradient times gradient times gradient times many. If it's a deep network, and if the activation function is such that it compresses the value very sharply, then multiplying very small numbers over a very long length of time, okay, 0. Let's say maximum values are 0.1, multiply 0.1 100 times, then it becomes almost 0. Okay, so you have a gradient vanishing problem. It can be exploding problem, and so on. So in a very deep network, in some cases, which one to choose, and these are also defined by like which ones you use and so on. Okay, so as such, it's a hyperparameter. You will learn it from the data, from the type of network you're using and so on. So this itself is an interesting research problem in itself. Which ones are the best for which problem and so on. Okay, so so as such, what we know is that deep neural networks are highly nonlinear. Okay, but they are made of simple functions. Okay, so at any given step, this is what is happening, right? So as I said, it's a pretty simple, right? Just one function is being applied. These functions are also quite simple. Okay, this is sigmoid 1 divided by 1 plus e to the minus z. It's a very simple function, as we know. Okay, so some function is applied on linear combination plus some the bias term b. That's it. Okay. So so what happens now is that overall this is nothing but a function. So from a maths point of view, neural networks are nothing but one big function. Okay, it's just that it's nested. That's it, and it is a parameterized function. That's very important because we are doing machine learning. Okay, not a deterministic algorithm. We are doing machine learning. We are producing the algorithm. Okay, so we are generating the program itself. Okay, that will solve my problem. So machine learning is slightly different. So that's, we have these parameters in the network, and these parameters will get tuned to the problem that I'm trying to solve. Okay, so as such, we are developing the program itself. So these weights are learnable depending on the labels. We make a loss function, we use gradient descent, we tune the weights, just like I showed you in the last class. Use gradient descent, then we need gradients, and chain rule we will use. That's the backprop. That was a interesting breakthrough. I will quickly go to that later on. So these are the choices for the activation function. Okay, so this is sigmoid. So there are good and bad properties as such. From if you look at from maths point of view, this is nice differentiable function. The values are between 0 and 1. Okay, so all these in some sense do some form of normalization. Okay, the input z may not be within 0 and 1, but the output goes between 0 and 1. Okay, so usually when we are dealing with classification problem, then it may produce values like 0.9. Then you say, okay, there is a 90% probability that it's a cat, or okay, so that's how you determine, because if a value between 0 and 1, you could also see this as a probability distribution. Okay, so but you can also have tan h. Okay, not necessarily has to be okay between 0 and 1, and you can also have ReLU. Okay, but we can see that there is a non-smoothness or a kink here. At 0, it's not differentiable. But since the function is so simple, derivative can be still defined quite well. Okay, at 0, you can still say it's 0, and otherwise you can say that the derivative is 1. Okay, so usually it's not that of a problem. Okay, still, so it's quite popular. And so basically here as well, as I said, there are many choices depending on the problem at hand. So as I said, deep neural networks have input layer, output layer, and then we have hidden layers. Okay, so these are the hidden layers, and we can see overall everything as a function that takes the k features x1 to xk, and all the weights everywhere I can combine them and call them as one big W set of all the weights. Okay, this is very simplistic because the weights apply sequentially one after the other, but we can combine all of them and say these are all the weights. So essentially this is how things are very compactly. I get outputs. My notation for the output is y1 to yl. Okay, in some text they use y as the actual level, but there is a slight change here. This is the output that is produced by the deep neural network, and the desired output I will use d. Okay, so function f operates on a set of inputs to produce a set of outputs. So as you can see, we have a generic L. It may produce L outputs. Okay, so there may be L classes I want to predict, right? So there may be L objects, and I want to predict which one of the L. Okay, so or if you have just to predict one output, okay, then you can have just y1. Okay, so it depends. It's a multi-class problem. It's a binary classification. It depends. So obviously, as we have seen, changing W will change our prediction function. Okay, so everything now depends on W. Okay. We may also have something called softmax activation, especially when we have multiple classes. So softmax is defined like this. So as you can see, softmax vector activation are a vector. Okay, so these are vectors of the same length as the output. So in this case, y will be a vector of length L. Okay, so this is softmax activation in its use, because in the final layer I want to see L outputs, and each output is telling me the probability of the first class, probability of the second class, probability of the third class. So as you can see here, this will be length L vector. Okay, so so here we sum over this. So basically we are normalizing this in the denominator. We are taking zi ith, but then we are normalizing it by summing up all, and we can do it for all the i's. Okay, maybe ideally I should have a yi here. So basically each yi is exponential of zi, and then divided by the sum of all exponential zi. Okay, so the typical notations that we use, because in deep neural networks the only confusion that arises is with the notations. Okay, otherwise it's not a big deal. Okay, so the only thing when you try to program this, you have to be a bit careful with the notations, okay? So which W you choose between this, what is the notation for W from here to here and so on. So the only difficulty is notation here, okay? So we can set some notation here. So let us say all the weights between the input and the first hidden layer is W superscript I, okay? The W super I, and Ij denotes the edge from I to J, okay? So let us say this is I and this is J, so this is your weight Wij, and these weights are before the first hidden layer, these weights are before the second hidden layer, these weights are before the third hidden layer, W superscript 3, and so on, okay? So, and bias, since there is only one bias at each layer, we can just say B superscript 1, and we can say B superscript 2, and so on, okay? So, but where it's going is denoted by J. So J is the second. So bias is also connected to all the neurons, obviously, okay? So the J is telling me where it's going, okay? So we have this notation which is pretty standard, and we call these intermediate outputs as Y superscript 1, and we call this output as Y superscript 2, Y superscript 3. But again, this is for the first output, okay? So Y superscript 1 is this one, Y superscript 2 is the second one, okay? And Y superscript here 3 will be this one, Y superscript 1 and subscript 4 will be this one, and so on, right? So that's how it works. And similarly here, if you see Y superscript 1 is the first one, Y sub 2 is the second one, Y sub 3 is the second one, third one, and fourth one, and so on, okay? And these are the output from this neural network for the L classes. So I have capital L as outputs, okay? So I guess, yeah, that's all for the notation. And with the notations that we have, since we started for the first hidden layer as Y superscript 1, we can, for the consistency of the notation, we can say this is Y superscript 0. Okay, in the algorithm it will be easier. I can run the loop from 0 to the last layer. So input you can call Y superscript 0. Okay, so that's why we have Y superscript 0 are nothing but the inputs, and Yi are nothing but Y to the n. We can say this last one is the capital N. Okay, all this is just for writing algorithms. You want to use some consistent notations. For loop goes through 0 to n. Okay, you don't want to like separate these, okay, because the more or less the operations are similar. Okay, so weight of the connection between the ith unit of the kth layer and the jth unit of the kth. Okay, there is some issue here. So ith unit of the k minus 1th layer, I guess. Okay, because the way we are writing is 1. 1 corresponds to the first hidden layer. Okay, so it will be k minus 1 here, and this is the kth. That is fine. Okay, so k minus 1 to k weights are denoted by w superscript k ij. Okay, I to j. Okay, and bias again, as we have discussed. Now then, usual notations is xy, but I'm using xd. Okay, d is my desired output. So then my first sample x1 and desired output d1. Second sample x2, desired output d2. So when I'm passing these samples, I will pass x1. Okay, x1 goes here. All x1. X1 is a vector, right? X1 goes in, and it will produce some y, and I will check that whether how close it is with d. If it is exactly same, no loss, no gradient is 0 because loss is 0. No gradient updates, weights are not updated, I'm happy. Then I pick the second x2, which is a vector that goes in. It produces some output. This time, let's say it's not matching with the corresponding d, which is d2, and then the loss will be some value. Then gradient will have some significant value, and then if I do w minus grad of the loss with the weights, there will be some update for the weights. So this process continues. Okay, you pass one sample, check, tune the weights if required. Okay, and again, this process itself may vary a little bit. Okay, whether you want to do it one sample at a time, or whether you want to build two samples at a time. If you pass two samples, then there will be one loss term for the first sample, one loss term for the second sample. You add those two losses. So now gradient will be for the two sample losses. Gradient could be for the 3 sample losses. So that depends. That's called batch. Okay. So how many batches of the sample you want to input? Okay. So then you have a batch, mini batch gradient descent. Usually batch we call it full batch, but you can have mini batch gradient descent. So that's also it depends. Okay. So until if you don't use the full batch, then it's kind of stochastic because even these samples that you pass are not necessarily one after the other. Okay. You pick these samples kind of randomly. So, and even if you want to go for the mini batch, you usually pick this mini batch samples randomly. So hence the gradient that you will compute will be like stochastic. Okay. So because there is a random sample, right? So I'm computing gradient of the loss for a random sample. So it will gradient will behave like a random variable. Okay. So hence the learning process will be stochastic gradient descent. Okay. So more or less we are okay with the notations. So multi-class classification I have already kind of discussed. It seems like a bit repetitive here. So for multi-class classifier with n classes, one hot representation will have n binary outputs. So it may happen that, let us say, you use the softmax. Okay, softmax is not necessarily one hot. One hot means that your vector has only one entry where it's typically 1 and all other entries are 0. This is called one hot representation of vector. But if you use softmax, it will give you probability value which is not necessarily one hot. It will give you 0.9, 0.1, 0.01. Some will be 1. Okay, it's a probability, but it won't be one hot. Okay, so if you pass a softmax, it will give you a probability distribution that 90% I think it's a horse, 10% I think it's a cat, and others are 0. Okay, so in multi-class, one thing you remember is that you usually use softmax, and again the losses that you will use depends on that. Okay, so softmax vector activation is often used as the output of multi-class classifier, and obviously these softmax outputs should sum to 1 because it's supposed to be probability. That's it. So here in the slide, okay. So where can I use multi-class classification? Where I'm learning to predict which 0 to 9 handwritten digits I want to predict. Okay. So this is a multi-class classification problem with 10 digits with 0 to 9, and I'm supposed to predict. Someone will give me some handwritten digit, and I have to predict which one is that. Okay. Which digit corresponds to that. Okay. So we are given number of training data instances, images of digits along with information. So this is supervised learning problem, obviously. So during training, I will know exactly which one. Binary one will be just whether it's 2 or not. Multi-class will be out of the 10 which one. So training data in handwritten digit will look like that. Okay, you will be given image. So this 5 is an image set of pixels. You can see them as a vector, and this vector can go as an input into the deep neural network, and you will see whether the output was 5 or not. If not, then use gradient descent, tune the weights, and keep doing this. You train your network with this level data, and some point it will learn. Okay. Obviously, as a formality, we define some loss function. Okay, so again, loss can vary, right? So loss, there are many choices of a loss. Loss is nothing but how I measure the similarity, right? My network is producing some output, and there is a desired output. How do I compare them? Okay, that itself is an interesting problem, right? What is a good measure? Not all measures are the same. Okay, so in fact, when we will go to generative modeling, we will see so many losses to compare the probability distribution. I have Taylor divergence, I have Jensen's divergence, I have Earth mover distance. Total variation distance, it's like so many are there. Okay, so in the lecture notes that I'm supposed to release, there is one chapter just on probability measures. Okay, so or the distance metrics. Okay, so here in neural network also obviously we are training. So this dive stands for generic loss. Okay, I call it divergence. Okay, this is a very generic term I'm using. That the dive is for some loss. So for example, a dive could be just 2 norm. Y is the output from my network, and D is the desired output, and I'm using just 2 norm. So you're familiar with the 2 norm, and I do a square because it becomes a differentiable. If you don't do a square, it's not differentiable. Okay, so squaring makes it differentiable, and if I indeed differentiate, then differentiate this loss with Y. But of course, when I'm training, I have to differentiate up to W, so I have to go to the chain rule. But I'm looking at the first step. Is it already differentiable with Y? Say chain rule will say, okay, after Y, go to the previous post activation value, which was Z, and so on. Okay, so this will follow. But the first step I want to check is it differentiable with Y? Okay, and indeed it's the case that it's very simple. 2 gets cancelled, and it's yi minus di. This is the ith component of the loss. Okay, because gradient as such, y is a vector. Okay, so I mean y, the loss is a number. Loss is a number, but it depends on yi, and yi is like a vector. Okay, depends how big the vector is. So it depends with respect to yi, the ith component of the y. I'm taking the derivative. So this is differentiable, but if it's a binary classification problem, then your output will be 0 or 1. Y will be 0 or 1, and desired output is also 0 and 1. For such cases, cross entropy is preferred loss for binary classification problem, and this is defined like this: d log y, 1 minus d, 1 minus y. Is there a mistake here? Someone can point out? There's log missing here, right? Yeah, so there seems to be a mistake here. So it's minus d y and minus 1 minus d log of 1 minus y, right? Okay, so this is binary cross entropy. So if you have binary classification problem, you are suggested that you use this rather than this. Okay, there are certain losses which are well defined for a given problem. This is also differentiable because log is differentiable as such. So this is nicely differentiable. And we may have a few other losses if there is a cost, if there is a case where the desired output is 1 hot. As I said, 1 hot vector is a vector which has only 1 place 1. So this is the 1 hot vector. It's a multi-class classification problem where I just have to predict one out of the let's say k classes. But if I use a softmax, then my output will be probability distribution. Okay, in that case. So you may use cross entropy. So how if you use a cross entropy between 1 hot and actual output, one possible loss is this: you sum over di log of yi, and di has 1 at the cth. So only the cth term will remain. Okay, so basically your network is producing this yi, but ultimately your loss will only be log of yc. Okay, so eventually it looks very simple loss. So it's a multi-class classification problem. The desired output is 1 hot, obviously, because it knows for sure that it's a cat at the cth. I mean, it is predicting cat, which corresponds to the cth class. And what I'm producing by softmax is a probability distribution. So how can I compare probability distributions which are values from 0 and 1 to 1 hot, which is just 1 at one place? So this could be one loss that you can use to compare 1 hot with a probability distribution. You can use something like that. And this is also differentiable. Obviously, dy loss, derivative loss with y I is just is minus 1 over c, okay, for the cth component. Okay. In training, it has been found that keeping this completely 0 is not good for the gradient descent. So there is an idea of something called level smoothing, where rather than keeping it 0, you put some small value, okay, epsilon. Epsilon is supposed to be very small, but not 0. Okay. So this is called level smoothing, and it helps numerically in when we use gradient descent. More or less, all the components see something rather than nothing. Okay, so that is found to be useful in some cases. Okay, okay. So these are very basic. I described deep neural network. I described input layer, output layer, hidden layers, hidden units, activation functions, sigmoid, ReLU, tan H. Okay, properties, differentiability, non-differentiability. I discussed multi-class classification problem, and I discussed binary classification problem. Typical loss is the 2-norm loss, but then for classification problem, you should rather go for binary cross entropy or the usual cross entropy loss when you compare 1 hot vector with the softmax output. Okay, and there is also something that is found useful when you are working with multi-classes. You use level smoothing. Okay, so these are the things we keep in mind. These things also play a little bit of a role in generative modeling. One of my students was working with something like this, and he did some level smoothing, and it was useful in GANs. Okay, so we will get into this usefulness of these things also in generative modeling at some point. Okay, now we come back to the network itself, and we have developed some notations, right? So input layer, we call it y superscript 0. Next, the first hidden layer, we call it y superscript 1 according to our notation. Third one is y superscript 2, and the final one we call it y superscript n, which is the actual output, I believe. Right? So what happens, right? So how does this network process the input? Okay, and this is called forward pass. Okay, we will see why it's called forward. Then there must be a reason for having backward pass, maybe. Okay, that's why it's so. We have input. Okay, this input goes in. Okay, and then just like MLP, what we do a linear combination of the input. So your input is y0. Okay, and y0 individual components of y0 are let's say ith component. So these are your y0. And weights of this layer, the notations that we used just before the hidden layer first one, we denoted it w superscript 1. So this is w superscript 1, and the entries are ij. So you are doing linear combination of these inputs with the w to get the first output. Okay, so this is your just before these z are called pre-activation values. Okay, just before that, just before f is being applied. So these dots that you see, these are the z values. Okay, so these are z superscript 1. Z superscript 1 will be for j equals to 1. Okay, Z superscript 1 2 will be for you put j equals to 2 here. Okay, so this is your linear combination just before the activation. Now next step, if you see, y1 is now obtained after now I apply the activation function. So now I have applied activation function f1. F1 is activation function of this layer. Okay, so as you can see, I may change my activation function from layer to layer. Okay, and this is also quite common. Okay, you will see someone defining in Python code sigmoid. Next they say that let me try tan H. So which combination to use also in some sense is a hyperparameter. But one thing you notice is that within the same layer, we don't change the activation function. You see F1 all the way through, right? So there is F1 for all the hidden units of the first layer. F1 is kept fixed. So you will see this is typically not changed. In fact, I have not seen changes so far. If you have seen anywhere, but yeah, so far what I have seen for each layer, you don't usually change the activation function. Okay, so this F1 is kept fixed. So that's how you get y superscript 1. So this is your y superscript 1 value. These dots are now your y superscript 1. So you can vary z. Okay, so j1 is your first one, j2 is your second one here. Okay, j3 is the third one, and so on. Okay. So as I said, it's only notation game. Okay, it's not a big deal. Neural networks are, I mean, if we will see transformer and all, they are a little bit interesting, but the basic neural network is not necessarily complicated. Okay. CNN is also a bit interesting. Okay, so we get y1. So we get these values. And after that, we do the same process. There's nothing changing here anymore. Basically, this is the recursion that you will apply again on the 2. Okay, so basically you just change 1 by 2, and basically you increase the indices by 1, shift the indices by 1. So 1 becomes 2, 1 becomes 2, and 0 becomes 1. That's it. It's when you apply for loop, it's very simple to write a for loop. In the for loop body, you will have this parameter, and they just gets increasing. Okay, so basically this feed forward is nothing but just a recursive application of two operations, linear combination and activation. Now you may say, why are you doing all this childish compute Z, and then why not do it in one shot, right? At least between the two layers, why not I go directly to the Y? Okay, so basically, so what I'm saying is like, why should I compute Z anyway? I will just put this guy in the Z. That's it. So I do linear combination activation, done. Why should I bother these intermediate values? Why should I bother? Why do I bother keeping these intermediate values? Last class, training, backpropagation, chain rule. This helps. There is a reason behind that. Okay, this looks very simple and childish. Why I'm doing all this simple calculation storing? But actually, it helps in the chain rule, because in chain rule I will go step by step. Why I will go step by step? Because differentiation with just the immediate one is easier. Okay, differentiation with just the previous one is easier. That's the whole reason. So I will save these values. Okay, you will not throw these values. You are not going to just save the output values. You are going to save all the intermediate values. So there is a memory complexity involved here. But typically these layers are not very big. Usually I don't see them going to 100 also. Okay, usually they go up to 10, 20, 30. But again, it depends. If you use some complicated networks like transformer, things really explode quite a lot, especially if you go for LLM. But in typical scenario, it doesn't go more than 20, 30. Okay, so and the hidden units also are not usually too much. Okay, I mean your input can be very big, right? So your input needs to be processed, but then it gets compressed. So these number of hidden units does not have to be same like it's shown in the figure. Okay, the number of inputs does not have to match the number of hidden units of this layer or for this layer. In the figure it's shown to be same, but it does not have to be. Your input may be very big. You take the hidden layers to be smaller. It's fine. Okay, it will compress. In fact, compression is a good idea in deep learning anyway, because it reduces the noise and it focuses on the important features. In fact, this is one of the things which will become primary also in the generative modeling. So we will use latent variables. We will use compressions. So it does not have to be same. Okay, everything still works. It's just that you have this sum has to be changed. Okay, a little bit. So you can say the depth. Okay, so this is also called depth, d1. So you just, if the change in length, you just have to sum d1, depth of the first hidden layer, d2 here, the sum of the second hidden layer, and so on. Okay, so it is possible to just change even this length. But again, the recursion is the same. It's just the summation changes. That's all. Okay. So as such, feed forward is a very simple process. Okay, no complications, at least in the deep neural network that we have right now. Okay, even for others actually, feed forward is always easy. Okay, it's not a big deal. CNN it's a little bit thing. RNN is still easy. There are some attention calculations. If I go for attention based models, transformer is a little bit complicated. Okay, so we'll see all those. Okay, so I'm going forward or backward. Okay, so this was our feed forward. And basically, this slide is telling you the final thing, because everything was recursive, no point in saying everything. So it's saying that, look, what happens to the final thing? The final thing, yn is activation of the zn. Zn are these guys, and these zn themselves were computed from previous yn minus 1. A linear combination was done. So linear combination was done to get zn, and zn, when we had this, we did the activation as a final step. So it's the same process. So as I said, it's a very recursive process. So I can just apply a for loop. So for loop j equals 1 to, okay, k is also there, sorry. Okay, sorry, yeah. So k is also there. So k is 1 to n. N is like the number of layers. Okay, so k goes from, according to our notation, it includes the input and the output. Okay, so and we are using 1, but then according to our notation, y0 was there, right? So we did k minus 1 so that it starts from y0 for, no, this is k, sorry. So k is like this. So k is like this. So this is our outer loop, and inner loop is about this depth. Okay, this depth. So basically, at the for k equals to 1, you will compute j superscript 1, and you have w superscript 1. You know these weights, and y superscript 0. You have these inputs, so you get this linear combination, and then you do the activation to get the y superscript 1, and j is like the layer width, right? So this j is the second argument w, right? So second argument of w is like how many in this layer, right? So this will be the layer width, right? So basically it's saying how many hidden units are there. What is the depth of your layer? So that many let me see if the notation is correct. Yeah, that's correct. So for each j, I have to sum over I. So basically these guys are the I, and they will sum for j equals to 1, they will sum for j equals to 2, they will sum for j equals to 3. Okay, so okay, so that's it. Basically that's it. It just goes up to n, and you get the final output, right? So y superscript n is what you're looking for, and this will indeed give you the final output. And we can write the algorithm now. feed forward, which is one of the simplest algorithm you can think of. So k equals to 1 to n is the layer, first layer, second layer up to n, right? And the 0th one, j equals to 1, k equals to 1 will denote the y0, and which is indeed our input, so that we have got it sorted out, and everything works. Okay, so not a big deal. And we have used dk. Previously we saw layer width, now we denote it by dk. Okay, so dk is our number of hidden in its first layer, number of hidden in its second layer, and so on. Okay, so it's a very simple algorithm, feed forward network. And as I said, these guys are important. You save this. Okay, you don't throw away this. You are not only looking at the final output, because you have to train these guys, right? So you will need these. So you will store them. Now I will go through the derivative, but very quickly. Okay, so derivative, if you are familiar with the calculus chain rule, then derivative is also easy. Okay, because essentially it's a chain rule. It's just that now there are many dependencies, right? So if you know in calculus, if there are k values producing one value, what will be the derivative, right? So because the output is now a function of these guys, right? So what is the derivative of this with respect to one of these guys? So these are the calculus things you have to see, like functions of multivariable. Okay, how I take derivative with one of the components of the variable. So these are the, sometimes this guy is affecting k in the future. Okay, so how will you take derivative in those cases? Okay, with respect to this guy. So there are two main cases: this guy like this, or these guys like this. So if you know how to compute derivative, and in these cases, more or less you are sorted, because this is what is happening more or less everywhere, because these guys are affecting everyone, but then these guys are being used to compute one of the values. Okay, so that's what more or less is happening. Okay, so as long as we know this, it's easy. Okay, so let us see the overall plan. Okay, because anyway these things are computed by the library, so you just call a backward pass in the library, and it does all the gradient calculations for you. Okay, as I said, there is only one place where I will need a little bit of idea about backpropagation, because that is used in generative modeling, but otherwise I don't think I need this. Okay, so let us see how to compute the derivative. We compute the derivative because we want to tune the weights. Okay, we want to compute the derivative with respect to the weights. Okay, but to go to the weights, we use chain rule step by step, so that it could be computed cheaply. Okay, rather than symbolically computing all the derivative. So your first step in the chain rule is that you go to the last one, and you have, in the last one you have obviously the loss function, which is divergence of y comma d. Okay, y is the output from the network, and d is the desired output, and you will now compute the derivative of your loss with the first dependency. First dependency is yn. Then, having computed the derivative of the loss with yn, the chain rule will say that now you go ahead and compute the derivative of yn with zn and multiply to that. Okay, and then the dependency of zn is on yn minus 1. So then you will compute the derivative of zn first component, zn second component with respect to yn minus 1 first component, yn minus 1 second component, and so on. Okay, then you keep doing this again and again. Okay, so that's the idea. So that's how we do the derivative of the loss with respect to yn. Then we look at derivative of the loss, derivative of yn with zn, and we keep multiplying those. Okay, so and then we keep doing that, then we yn minus 1, then zn minus 1, then yn minus 2, zn minus 2, keep doing that, you arrive at 1. We did a lot of jump, there was a dot here, so we did a lot of jump. Now we are at z1, and then basically you will stop at the weights. Okay, because you are only interested until the weights, and weights are there until the first, just before the first hidden layer. You will stop here obviously. So that's the notation we use. What we need is w superscript 1, so derivative of the loss all the way. So this is the most completed one, right? Because for computing the derivative you have to go until here, whereas if I have to compute derivative I will just stop here for the weights here. But this whole network is parameterized by all the weights obviously. So I will compute all the derivative with all the weights and make them into one big vector. That's it. I have to stack them. I have to stack the derivative with respect to these guys. I have to stack after that derivative with respect to these guys and combine them into one big vector. Okay, and then do the gradient descent. Okay. Okay, so this is our this is what I said. So we have the loss. The first step is the loss depends on yn. So I took a derivative with yn. Yn has how many components? 2 components. So I will be, for 1 is this guy, for I equals to 2 will be this guy. Okay, so I have those derivatives. Now I go to zn minus 1, because yn depends on zn. Okay, and zn has how many components? 2 components. I guess we are looking at this component because there is an arrow here. So we are calling this as z1. So this is z superscript n, first component, and this is second component. So let us focus on the first component. So first component depends on yn first component. Okay, so yn first component only depends on zn first component. Okay, and that is later used in the derivative. So sometimes this mapping helps. Okay, this is all about mapping. That's why they make this graph. Okay, dependency graph. Okay, so this is, we have we have y and 1. So we have y and 1, and that was result of only z and 1. Okay, no other thing, z and 1, and this y and 1 had an effect on the divergence loss. So if I'm just focusing on derivative with respect to z1, then my graph, dependency graph, is like this: divergence with respect to y and 1 times derivative of y and 1 with z and 1. So that's what we did, right? The derivative of divergence with y and 1, and then y and 1 with z and 1. Okay, so that's sorted. And due to symmetry, z and 2 will also be same, because z and 2 is just same. It's just that now you will pick up y and 2, this guy. So for z and 2, you have derivative of divergence with y and 2, and derivative of y and 2 with z and 2. Okay, so far this was simpler case because one-to-one dependency. Okay, okay. So we know derivative calculations until here. Okay, and what do we know, right? That's where the backpropagation, saving the data, all this helps, right? So this is already known. Why? This is known, right? Why it's known? Because y and 1 is known. Okay, so divergence will be some function. Okay, so let's say del y and 1, right? And this is the divergence function. So I know how to take derivative with respect to y and 1, and after taking the derivative, it will be some expression in y and 1 and the desired derivative t, but d is already given to me. So basically everything is known here. Okay, even if there is y and 2 also somehow present, that is also known to me after doing the derivative. Whatever is there is known to me, so I can compute that. So this I already computed. Okay, so that's done. And if the loss function is simple, this calculation will be simple, because derivative will be simple expression, and then I can just substitute the values. Okay, and this is let us look at this. What was y1n, right? So y1n is the post activation value, right? These guys are the y1n, right? So these are post activation. It's like after applying the f. So y and z, how are they dependent? So y and 1 is fn of z and 1. Okay, so basically this derivative is nothing but this, right? Derivative of fn prime z1n. So this, assuming that this was some simple sigmoid or whatever, this is also very easy to compute. So I have those values as well computed. So you are here, okay, and then so this z1, the fact that I saved it in the forward pass, I'm going to use that now. Okay, and these are simple functions after derivative also, so I can use them. Okay, because I've saved this data. Then we can go for other values. For instance, derivative with okay, so we have this. We have what we did is we just substituted this guy with the derivative calculation. So that's why you see. So nothing really changed. It's just that we replace the derivative with z here, and we can do it for all the z I, right? So you replace by I now. Generic I will be calculated like that. And now what is interesting is now we come to the weights, right? Now these are the weights that are used in gradient descent to tune the weights. So this blue one, let's say, is 1 1. Okay, so this is nth. This is nth layer weights, and our numbering is like this, 1 2 like that. Okay, so 1 is to 1 of 1 to goes to 1. So that's why this is 1 1 weight variable nth. Okay, just before the nth layer. So now this is exactly what we need in gradient descent, right? So if we look into the weights, right? So these weights are here, right? So these weights, how are they affecting the loss, right? So loss with respect to z we have computed in the previous slide. So we can now say that we have already in hand derivative of the loss with respect to z. So we are already here because we had done those calculations. Now only thing we have to see is, and we know that this z is dependent on the W11, because W11 a linear combination. So it is a little slightly tricky now, because W11 these W linear combination will happen. So there is not just one-to-one dependency now. Now there are like multiple W's affecting this, and what we are really interested in just one of that. Okay, so this is very interested in one of that. So let us see what happens in this case. So this we already computed. So that's why we straight away wrote this, and then this. So to compute this, we have to see how z1n was affected. So z1n was w11 yn minus 1 1, and plus some other terms. We are not writing the other terms because we are not bothered by anything other than w11. So we just write, because if I take derivative, those will be like constant, because we need partial derivative with w11. So just wrote other terms. So basically, if I take derivative of zn 1 with w11, only what will be there? Yn minus 1 1, right? So that will be the outcome. So we will replace this by that, and y n minus 1 1 was actually saved during forward pass. So basically all these values are there. So I substitute that directly here, and this was already computed previously. So basically we have now the function value with 1 1. Now we can apply the same thing for w12. So w12 again we apply the same thing. Then we will have I guess y2 there. Okay, so So basically we will now generalize this for any ij. Okay, so for any ij you can see that this will be yi and zj. Okay, and for bias term y is 1, so there we don't have to do much for the 0th one. Okay, so that gets anyway adjusted, there is nothing much to do. Then the process kind of repeats. Now you have computed the weights, now you are going to fetch the derivative with respect to these guys, right? So now you will do the similar steps again. So now you want to compute the derivative with respect to yn minus 1 1. Let us say this guy. Now you have to see how this guy affects the forward computation. So now you can see this guy actually branches out here. So this is affecting this one, this is affecting this one, and then those are affecting the future results. So there is a branching there. If there is a branching, then I am supposed to calculate the effect of these through both the branches. Okay, that's why I have to now go through both the jets. Okay, that's why you see sum over the z, and then this is j1, zn1 is also there, in the sum zn2 is also there. Okay, so zn1 is there, zn2 is there, because there is a branching out. When there is a branching out, you have to sum, okay, the effects for both. Okay, so so in this case you see the sum, and all other values are already calculated. Okay, so basically all the values are known to you. This is already known, and if you see j by dy, right, so again you see again you look into this term and see how zj and yn minus 1 1 are related. So you know that z was linear combination of the y. So you wrote this, and only thing you have to, in the sum you have to look for, because you are taking derivative with y minus 1 1, you only look at that term. Other terms don't have. So if you take derivative of z and j with y1 n minus 1, then you are left with wn 1j. Okay, a little bit of detail is there, but overall it's simple. Okay, so that way you can compute for 1, but you can generalize this for all. So this was y1, you can do it similarly for y2. This 1 becomes 2 now, this 2, and similarly 3, 4 thing. Basically recursion was until here. Now things just repeat just like that. Okay, because after that these are the similar steps we have seen before. There is one-to-one dependency of this guy. There is one-to-one dependency of this y calculated for the z, just like there was one-to-one dependency of the y calculated with the z. So there will be no sum, nothing like that. It will be repeating in the same way. This whole block, the way we computed, and now it will get repeated until the yn minus 2. Okay, so more or less that's the repetition. So I can just skim over these things, and similarly if I'm computing with this y minus 2, then again we see the sum, because it's like branching out, and then we keep doing this, and we keep doing this, and then so we basically we go until the end, and we fetch the weights of the first layer. Okay, that's all. So we will only focus on the weights derivative of the loss with respect to the weights, because that's the only thing that is needed. Other intermediate ones were just to help. Okay, so that's it. That's backward. That is called backward propagation. Okay, backpropagation. And although this looks like a simple idea, but this was one of the important insights that was needed, that I will save this intermediate values and use this in chain rule. Okay, so this made the backward propagation tractable. Okay, so this is the full algorithm. I let you go through this algorithm, and maybe you can do some small exercise just to kind of revise these things. So I guess I will stop here. If more is needed, I will come back to neural network again. In fact, it will be needed at some point. I will need RNN, attention based RNN, then transformers, even CNN. But up to here we keep it like that. Now we are back to generative modeling. So okay, so in the generative modeling, our goal, given a sample that I pick from a given distribution P, okay, P is unknown, obviously, that's the whole point. How should we learn the distribution P, basically? Okay, so we have seen in the last class, one thing is maximum likelihood estimates, but then when we do the maximum likelihood estimates, we have seen that that we may use any distribution. Let's say normal, it's a 2-parameter network, then let's say independence assumption used, and we have tried doing that, and we saw that independence is not a good idea, because it's not like tossing coins and each coin toss is independent. So that's not a good assumption for images. Okay, images pixels are dependent. Okay, so then we said in the last class that why not try chain rule. Okay, if there is a dependence, then I'm thinking of pixel x1, pixel x2 dependent on x1, pixel x3 dependent on x2 and x1 and so on. Okay, so even that can be order exponential. We have seen that 2 to the n minus 1, because if we see that as the pixels are increasing, the dependencies are also increasing quite a lot. Okay, so the fourth pixel depends on 3 pixel values. So I need 3 parameters and so on. So it's like 1 plus 2 plus. So this is still exponential. So that was, we left it there. Okay. So there are a few things I have developed and left it there as a puzzle. But I will give you an assignment where even if this is a simplistic idea, you can still do something with that. Okay. So just to develop intuition behind that. So so there will be an assignment on, even on this basic idea, and a further build up on these ideas would be let's say sigmoid belief network, because finding dependency, having seen 4 pixels, what could the probability of the next pixel, it's a complicated problem. Okay, so maybe I wanted to use some neural network again, because neural networks are the very good predictor. So there are ideas that use from say a sigmoid belief network, fully visible network, and then there are some recent ideas like pixel RNN and so on. So that will lead us into some of these ideas we will cover in the upcoming classes. Okay, so there is another view that I want to kind of describe, which can also show up in the quiz in a simple way. So assume indeed that in some way p hat is learned. Let me define some generative modeling problem. Okay, so generative modeling seems to be two-stage problem. Construct an explicit distribution if you can. Actually, some of the generative models don't require you to do explicit construction. You don't necessarily have to build explicit distribution, but let us say from overhaul, even if it's implicit, we believe that some form of distribution has been learned. Okay, so construct explicit distribution, and then describe a way how to sample from that distribution, because sampling is also important. You fit some distribution, and then I'm wondering, because this distribution is complicated one, you mixed many. Okay, so then I'm wondering, like, how am I supposed to sample from what distribution you have fit? So sampling is also another thing. So we can define generative modeling problem this way. Okay, we can define generative modeling problem as this: construct a function generator z that takes from z to samples x. That is, that maps the source of simple randomness, where z I can sample from easily from some known distribution, and somehow I get x hat samples which are from the distribution that I want. Okay, which is the p hat in my case. So p hat I learned from the data, let's say. So what I'm thinking of generative modeling is that I prefer to sample from some simple distribution z where I know how to sample, and somehow there is a map g that takes me to generating samples from the distribution that is where I train, maybe the cat distribution or something like that. Okay, so overall generative modeling problem could be seen like that. Okay, so overall generative modeling is a statistical problem. We have already known, because we estimate statistically the distribution itself. So we want to estimate the underlying distribution from the data. As I said, just to clarify from what I defined, let us say I learned to fit a normal distribution, and let us say I will sample from standard normal. Then there is a basic relationship between normal distribution with mu and variance sigma square from the standard normal. So if you take standard normal and you do sigma times z plus mu, then you indeed can generate samples from the normal with mu and sigma square. So this is just a small example where this is a simpler distribution, standard normal, and from there I may transform. So this is my G map that transforms to the required distribution, which was normal with mean mu and variance sigma square. Okay, so one can check this, that if z is standard normal, then sigma z plus mu is indeed PDF of a normal distribution mu and sigma square. Okay, it's a simple exercise. So so this is one thing, right? I know a distribution standard normal, let's say, sample from there. Okay, I mean, I'm not saying that you can't do it. If you have many libraries in Python, you can just say that this is my not standard, but this is some normal distribution. It will give you samples. Okay, so it knows a way how it will sample from there. Okay, but this is leading us to a very generic view. Okay, so I will prescribe this as we go forward. So what I'm looking for is a sort of mapping that takes me from known distribution, where I can sample very easily, to the samples of the required distribution. Okay, can we do that? No, can we do that? That's like that's the main thing. Okay, that's what we will do. I mean, in fact, that's what will happen all the time. Okay, whether we do diffusion models, ultimately we are learning. We will map everything to some normal distribution or standard normal distributions, and then we will just sample from there, and there is a backward process or transform, reverse process that generates images of the cat. So that will happen like more or less all the time. If we use GANs, then that's what is happening again. Okay, so GANs are similar. I take samples from standard normal or normal and starts producing the cat images. The generator does that. Generator have to give just the normal distribution data or standard normal distribution data, and somehow it knows the transform G that generates the cat distribution. Okay, so this is more or less what generative modeling is. Okay, I have a nice way to sample, but somehow there is a mapping that does whatever it does. Okay, and it does a push forward and gives me the required samples. Okay, so this is just a little bit of a definition of push forward distribution. We can also ignore this for the moment. It's very simple as such. It's saying that if I have to calculate probability of A which is in the Z, literally I can go back by the inverse transform by doing G inverse. So if I have to compute probability of this guy, then I can go back by applying the G inverse of the A which is subset of X, and I compute the probability from my Z domain. Okay, well, that's pretty much it's fine, right? I mean, this we can do that because here I know the PDF of the Z because it's my known distribution. So G inverse A will be some area in the Z domain, and there I know the PDF because it's a known distribution. I can compute the PDF values, which is nothing but integration. In the continuous random variable case, we have to do the integration, and that's it. So that gives me the probability for that. Okay, so this is just a way to define push forward distribution, but we will come to that a bit later. I don't think that's needed immediately. Okay, so let us see some example, simple example of how I can use this mapping from a known distribution and it starts generating samples that I need. Okay, there is a very simple intuition behind that. Let us see that. So let us say we have P samples, estimate P. So let us say we estimate P from some samples x1 to xn. Okay, and assume that they take finite values. So each xi's take finite values from 1 to k. Let us say k is 6. Okay, so die roll, and it could take values from 1 to 6. And I have taken n samples. So I roll the die n times, and I note what is x1. Oh, this time it was 2. What is x2? This time it is 3. Okay, so I roll the die. So k is 6, n whatever. Okay, so maybe in the example I took 7. Okay, so anyway, so let us see. So probability will be what, right? Probability of the ith die appearing, we know it's very simple, right? It's number of times I appears divided by the total number of possibilities I have. Okay, so this is simple to calculate from the data. Let us assume that I had 7. I have thrown the die 7 times, and out of that I observe 1 2 times. Hence the probability of occurrence of 1 is 2 over 7. I observed 2 on the die once, so probability of occurrence is 1 over 7. 3 is 1 over 7. 4 I never saw. 5 1 over 7, and 6 was 2 over 7. So this gives me the probability values. Okay, and what I'm trying to do, I'm trying to generate the behavior of the die roll, right? I'm trying to this die may not be, I mean, we don't know, okay, what type of die it is, but we want to kind of generate the behavior, the way it generates the data. I want to learn that. Okay, so that's the idea, right? So so I can draw the PMF and CMF values. So PMF values are this. Okay, I have just plotted. So this was I guess 2 over 7, 1 over 7, something like that. Okay, and 4 it was 0. So I've just plotted these values. Okay, histogram plot. Okay, so and then CDF values is a cumulative probability. So cumulative up to 1, I guess it's 2 over 7, and then cumulative up to 2 is 3 over 7, I guess, and so on. So CDF is, what are the properties of CDF? It's what are the property of CDF is needed, right? What is it? Is it monotonic? It is monotonic increasing function. What can you say about monotonic increasing function? Monotonic, not strictly monotonic. Okay, and what are the values, range of values of CDF? Range of value it takes 0 to 1. 0 to 1. Now tell me how I can build a generative model by looking at CDF. 0 to 1 samples. 0 to 1 samples. So how can I generate? Inverse. Yeah, exactly. 0 to 1 is easy, right? It's 0 to 1. I will just do uniform sampling, right? 0 to 1, I pick any number 0 to 1. Okay, and then look at where it hits. So let us say some value between 0 to 1. I could have maybe plotted it from 0 also, so that it indeed goes to 0, but that doesn't matter. It's a simple thing. So I pick any value between 0 to 1, and I look where it hits CDF, and then I go and give that sample to you. Okay. If there is a tie, then I may apply one more level of maybe still, let's say, uniform probability and say okay, because here there may be tie between 3 and 4. Let's say I say okay, take any out of 3 or 4. Okay. So since this is a discrete case, you may say, let's say 3 or 4. 3 or 4. Okay, there you may kind of say if it is somewhere in between, also you have to break the tie. So if it is, let's say, between 4 and 5 exactly, then you decide whether you want to say it's 4 or 5. So there will be symmetry breaking needed sometimes, but it will be rare. It will be rare that you will be exactly in the middle. Otherwise, you will take the minimum. So what can we do is that, let me do here also, because then it will show up in the video. So let us say I take this number here, right? So it's, let's say 0.56. It goes here, it hits here, and then I look at the corresponding sample, which is somewhere here, 0.2926 or something, okay, and since this is closer to 3, because the samples are just discrete values 1 to 6 on the die, I have to predict which number. So then I will say, okay, closer to which one? 3. So I will say, okay, your sample is 3. So just by doing sampling from 0 to 1, I'm producing the behavior of the die. Okay, each time I randomly pick, it is random. Okay, so each time I randomly pick, it gives me samples from the die. So this is one generative process. Okay, where we call it inverse CDF. So we basically do the inverse of the CDF to go back to the sample. Okay, so that's a very basic generative model. Obviously, again, for images it will be tricky because images are not that simple dimensional. So, but we will slowly build our intuition. Okay, we want to build our intuition step by step. Okay, so that's why I leave you at slight puzzles, but we will build on that slowly. So CDF's values are between 0 and 1. I've just written what we just did. CDF is invertible, at least, like, let's say locally, or we can break those symmetries. Can we use both the facts for generating data? Yes. So that's what we did. So we had this inverse CDF method. So sample Z 0 to 1 uniformly on the y-axis, draw a line parallel to the x-axis passing through the Z on the y-axis, and then assume that it intersects on some s, and then look at the point on the x-axis where it corresponds to the Z, and that's it. Okay, report x as a generator sample. So this will be one problem, let's say, in the quiz. Okay, and there will be one problem based on the chain rule also. So in the chain rule case, what I will do will be in the assignments. I will release one assignment because you may wonder how can I use the chain rule 1, but it is possible to do something with that. Okay, with small example. Okay, so I will prepare one example there, and this is so for quiz. You seem to have two ideas. One is inverse CDF, and one is using the chain rule. Okay, and the basic definitions you need to know. Okay, okay. So with this I will stop. I guess I'm on time. Okay, so see you in the next class.